Welcome back, class. So last time we were learning about the discrete time signals, and we learned about the different properties of the discrete time signals. And now we are going to start about the system properties and the LTI system, okay, for the DT signals. So let's start with the linear system, okay. So we have already learned these concepts in the signal and system, so we are just revising it for the discrete time signal. So let's say if we have a system which has an input of x1, so this is a system which could be performing any kind of operation, and it is giving us an output of y1. Similarly, we have an input x2 and that is producing a separate output of y2. Okay, so x1 is producing y1 and x2 is producing y2. Okay, now if I input these both signals together to the system, like I input x1 and x2, then my output will be basically the individual output sums. If I am inputting individual signals as a sum, then the output should be the individual signals sum. So if your system is having such properties, that is called a linear system. Okay, that the linear addition of the input signals will be equal to the linear addition of the individual output signals, whatever you are getting. Time invariant, like if we are having the change in time at the input side, okay, for example, if we are supplying x of n, we are getting the output of y of n. Now if we are making a shift here, for example n minus 1 here, so I should also get the same shift at the output. Okay, so if we are varying the input signal, time varying the input signal, we will have the same time varying shift at the output signal. So if our system is having such property, then our system will be called time invariant. Okay, that is independent of the time variation. Impulse response of an LTI system. Okay, we know that if you supply an input to a system, you should get an output. Okay, if your input, it could be of any kind. For example, input could be a unit step, it could be an exponential signal, okay, and it could be of any kind of other signals. Okay, if your input is an impulse signal, okay, then the output which you will get, it is called impulse response. Okay, the same like in signal and system. Okay, if you are supplying impulse as input your system, then the response of the system, the output of the system, it will be called as the impulse response, and we represent impulse response using this. And if we have any arbitrary discrete time signals, okay, we know that we can represent that signal as a weighted sum of the unit impulse function. Okay, so for example, if this is my one discrete time signal, okay, so basically these are nothing, these are just the impulses at the different locations. Okay, so basically any signal, any general discrete time signal, we can decompose that signal as the summation of the unit impulse function. For example, this is the impulse at 0, this is the impulse at 1, this is the impulse at 2, this is the impulse at 1. Okay, so if we add all of them, if we add all of these impulses, okay, with this signal, so we can actually represent our actual original signal. Okay, so this is a very important expression, okay, that any signal, it can be represented as the summation of the impulse signals, okay, from minus infinity to infinity or whatever range we are having. So now, so far we have learned that if you supply this input x1 of n to the system, you will get y of output. Okay, any kind of input signal. Okay, then we learned about if we supply the impulse, we will get the impulse response. What about like if we supply a general discrete time signal? Okay, if we supply a general discrete time signal, then what will be the response of the system? Okay, so we know that the general arbitrary signal we can write in this form. Okay, so now we are studying about that if you supply this as the input to an LTI system, okay, then what will happen? Okay, so basically we know that now what will happen? Okay, you will get an output, okay, relevant to your input, but you are also supplying input as an impulse. So if you supply input as an impulse, you know that our response will be impulse response. Okay, so basically what will be the change in the output response? Input, okay, it's kind of a constant here, so it's coming as it is, and here we have the impulse as the input. So when the impulse is the input, okay, the output will be an impulse response. Okay, so if we supply a general arbitrary signal to your input of an LTI system, the output will be in the form of the impulse response, because if for the separate impulse, shifted impulse, we will get the shifted impulse response, and if we are supplying with an input signal, so we will get that as the impulse response. So that is the output of a linear LTI system for an arbitrary digital signal. So we are just reviewing the basics. We will solve the examples relevant to this, okay, which is coming next, and we will solve the examples in the live session. Okay. So the next concept after the properties of the system, it was the convolution. Okay. So we know that if we have two signals, we can convolve them. Okay. So that we will get the so basically this thing which we are getting here. Okay, so basically what is happening here, that you have an input signal which is x of n, okay, and this LTI system has an impulse response of h of n. Okay, so basically in time domain, okay, these two signals are convolving. That the input signal this is convolving with the impulse response, and that's why we are getting the output of what? That x of n, we just change the parameter x of k, and we will get the shifted impulse. Okay, or like in continuous time, we may shift this one or this one, so it could become x of n minus k or h of k. Okay, so this is just a simple convolution operation, that a signal is convolved with the impulse response of h of n, so that we will get the output of this. Okay, it's similar to this one, like we get in time domain, h of t minus tau, okay, or x of tau, oh sorry, t minus tau into h of tau, okay, like in time domain. Okay, the convolution of the two signals. Okay, it's like this. So basically what is happening here, if you want to convolve the two signals, okay, for example, let's say, so this is your actually output. Okay, for example, let's say if you want to calculate the response at n is equal to 0, okay, so then y of 0 will be equal to, so x of 0 and h of, so h, it will be varying from the minus infinity to infinity. For example, let's start with the x of 0, it will multiply with h of 0, right, when k is 0. Then x of 0, okay, k is for example varying from 0 to infinity. Okay, so it will become x of 1 and h of minus 1. Okay, and then x of 2 h of minus 2. Similarly at the back side. Okay, so basically you have to multiply the impulse response and the input signal and then just add them, so that we will get the final output response. Okay, these are some examples relevant to the convolution which we will solve in the live session. Some basic convolution properties that if you are like having one signal, okay, so like if you convolve x with h, okay, or you convolve h with x, the result will be same, there will be no change. Okay, this is called commutative property. Okay, and if you have two impulse responses, okay, so what you can do here, there are two ways. The first way is you convolve this with this. Okay, so x of n convolving with h1 of n, you will get one response, let's say y1. Then you convolve this one with this one. Okay, you will get the output response. Or the second way is that you add these two, you convolve these two first, okay, and you make them one response, simple response, and then you just convolve with the input. Okay, so either you do this or do this, the results will be same, there will be no change in the results. This is called associative property. And then for the distribution property, if you have summation, so the first one is like you convolve first with this one, then with this one, okay, and then you add them. Okay, like x of n convolve with h1 of n and x of n convolve with h2 of n. Okay, and then you add them. That will be your results. Or the other way is first you add these two, so you will get this one. So in this case we will just convolve with this one. So basically these two are same. So this is called distributive property, that if you want to add, you can go for that, and either first you want to do the individual convolution, that will be also fine. Okay, so these are just properties, the convolution properties. Example about the convolution property, we will solve this in live session inshallah. Some more basic properties of the system. Okay, causality. Okay, this is a very important property of the system. So the causality of the system is a discrete time system is causal if the output depends only on the value of the input. Okay, so basically the system will be causal if the output does not depend on the future input. Okay, output only depends on the present or past value of the input. Okay, the output of the system only depend on the present or the past value of the input. Okay, then your system will be causal. Okay, for example, let's have a look at one example. Let's say this is one system. Okay, and so in this case, for example, if I put n is equal to 0, so I will get x of 0. Okay, so when I am supplying n is equal to 0, then I am getting the output. So the output is depending on the present value. So this system will be causal. Okay, let's say now if I have a system with this one, shifted time invariant signal. Let's say this is one system. Okay, so to check whether it's a causal or not, what should I do? I will just put n is equal to 0. Just check at one value. So y of 0, it will be x of 0 plus 1. Okay, now you are getting the value of 1. You are supplying n is equal to 0, but you are getting a value of x of 1, the future value. Okay, so you are getting the next value. Okay, you are supplying 0, but you are getting the value at 1. Okay, so the next value, the future value. Okay, so in this case it will be non-causal. These are more examples which we will solve during the live session. Causality. Okay, So it's like if you talk about the system, okay, or like if you talk about the LTI system. Now if you talk about the LTI system, okay, then the LTI system will be causal if its impulse response is 0 for all the previous values. Okay, so the LTI system, it will be causal, okay, if the impulse response is 0 for all the negative values. Okay, because we know that a simple signal is causal if signal is 0 for all negative values. Negative value means the signal is only existing when you are supplying the input, okay, only for the positive. Okay, if you are supplying the input at like n is equal to 0, then you will get the output. That is the basic definition of the causality. So the same is actually applied here for the LTI system, that if its impulse response is 0 for all the negative values, okay, then our system will be LTI system will be causal. Okay, and the next property is stability, which is basically the last property. Okay, so stability is like if you are supplying the bounded input, you will get the bounded output. Okay, so if you are getting the bounded output for the bounded input, then your system will be bistable. Okay, so if you are supplying bounded input and you are getting bounded output, okay, then your system will be stable. So if you want to check that whether your system is bistable or not, okay, so what you can do, you can just calculate the summation of the magnitude of the impulse response. Okay, so whatever impulse response you are having, just take the summation, okay, of that, and if the coming value is less than infinity, then your system will be stable. Okay, so why this is I am leaving to you, and we will discuss this, the reason for this, in the live session. Okay, and we will solve the couple of more examples. I am leaving couple of examples for you. You can try and check that whether that system will be bounded or not. For example, let's say if we have one system which is this one, so will this be bounded or not? Okay, stable or not? Let's say if we have one system which is this one, so is this system stable or not? Okay, so that is the end of this part of the lecture. We will solve the relevant example in the live session. Thank you very much for your time.